Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Right, and our next talk will be from Mike Harold from the University of Chicago and Argonne National Laboratories. I'm sorry, Mark Harold. I keep seeing Mike.
I know.
Somehow it got mixed up. I'm sorry about that. Talking to us about SIGGRID.
I'm Bob. Okay, so I'll be talking to you a little bit about a project that I have the luxury of talking to you about before we actually have gotten anything done on it. We just recently got funded for a little piece of it, and we're continuing to try to accrete money onto it so that we can actually move forward. Come on. It is? How come I'm not seeing it here? How do I move it back? No. I don't know how to move it back. Page up. Okay.
I think what's going on is your secondary display is showing everything. If you
Oh, I see. Here.
kill the secondary and then just flip it until it's showing the same on both.
How is it that you commandeered my laptop? Uh-oh. I think I know the answer.
Where are we?
I know. It's very hot.
They could have been in the house. Hey, Mark, they could have logged in from back there.
Yes.
It was actually...
Okay, so let's see if my... I'm just pushing buttons left and right. Huh? Well, it's not going past, I can't get above this one. 1 and character turn. I'm going to hit home. Escape. Start over. Oh, man.
F5. You have no slides before that.
Load again.
Don't save.
Don't save. Open. So something in that. Wouldn't this be horrible if this happened to you?
No, it always has to happen to you.
I found something.
Now go to the second one before you try to display it.
Okay. And what's F5 supposed to?
Play, just talk.
Okay, hang on. Let's hope these buttons work now. Okay, so the underlying sort of theme of this project is to try to get a handle on experiments that require data coming in from multiple modes of sense, so video, audio, and beyond. And what we're hoping to attack is building a system that can manage this data, collect it, archive it, allow for collaborative access to that data so that after the fact it can be annotated in the way that social scientists and behavioral scientists typically work with their data, and also provide interface to analysis tools. Now, we're focusing in this project on social and behavioral sciences applications, of which there are many. But there are also applications in fields beyond this into other domains. And from the computer science point of view, there are an incredible number of applications in trying to solve the research problems and making this kind of thing glue together nicely. So here's a list of some of the projects that we've been thinking about. It's a mixture of some of the computer science areas that we're interested in, as well as a number of the people who we're collaborating with in the social and behavioral sciences. So I'm not going to go through all of them, but there's neurobiology, pattern recognition involved in combining multimodal data in creative ways to try to understand, for example, what's going on in a room, events having to do with entry and exit of people, situations, whether there's a riot going on. Advanced display evaluation, and any number of other sort of human-computer interface sorts of issues. With a setup that we're going to be building, there'll be all kinds of data available for understanding the exact relationship between people's interaction with an object and the various cues they're receiving from other people and from the objects. This is pretty hard for you to read, but it points out that today in the sort of area of the social and behavioral sciences, they're limited in sort of a small focus in several ways. In one aspect, it's the sort of dimensionality of the problems that they can solve, and in another aspect, it's the sort of closed-off nature of the research. One group collects up some data, and they can use it, but that's not available to other people. This project aims to sort of blow out those borders in many different ways by, one, providing analysis and data storage, query tools to make it so that it's easy to manipulate large numbers of data sets, as well as making these available in a grid-like way to a large community that may not have been exactly directly involved in collection of one set of data, so that it sort of virtualizes the process of being able to do experiments after the fact. So the goals of the project are basically to sort of make a big change in the way these kinds of experiments can be done by putting this stuff out into digital form and paying close attention to how we sort of track the data, keep track of it, and allow people to access it. We enable a kind of experimentation that's not known in the social sciences and is only barely known in other sciences. It's sort of akin to a virtual observatory type science where data has been collected in the past and you can go through sort of virtual tours of sort of questions you might have to ask, pulling on data that's already been collected by somebody else. And we believe that these techniques will promote collaboration between various researchers at many levels. The existing way that these people work, they've developed a number of tools, and some of them are quite far-thinking and are kind of getting into the territory that we're talking about here. There are a number of public databases, and they're the kind of thing where a particular research group collaboration focuses on one sort of interaction that they're interested in. For example, communication between children and their parents, or communication between animals, whatever communication means in that circumstance. And then they set up a laboratory where they can take data and then they make that available as stream data or as stuff that you can download. And then there are various tools that allow you to annotate and analyze these things. VisSTA, the VisSTA, I'll show you a slide on that in a second, is actually particularly far along the road. They are thinking in terms of multimodal data and plugging in analysis tools that are not typical of the sort of things that the social scientists are used to using. Vision sort of processes where they're analyzing motion in the frames of the data. And then most of these tools, the speech, all support a means for supplying textual annotations, transcripts, various notations about what's going on, or even secret codes. Each of the different subfields has various notations that indicate whether or not some particular facial motion happened or whether this was a particular kind of vocalization, and those get coded up and marked for other people to look at. So here's a quick little tour through some of these things. This is the Macintosh version of this program, VisSTA, a visualization for situated temporal analysis. And its broad goal is annotation and analysis of multimodal communication sessions, okay? And it provides a means for you to view multiple streams taken in a given space and simultaneously view the audio stream that was taken in that place, and to do various manipulations and things like this, to do playback and synchronize and make markings on it. I think the stuff on the left, on the far right there are little places where annotations have been made to describe pieces of the speech that was happening. This is a very sophisticated speech analysis tool that allows you to apply a number of filters, analysis techniques, you can see some of the results of visualizations of various analyses that are done on it. It allows you to do synthesis of speech from a number of sort of abstract forms, manipulation of existing speech waveforms, and then labeling, which is sort of an annotation idea. Now, the SID grid that we're trying to build is something that is hopefully going to be able to take advantage of that body of work that's already been done. And so it has to be able to incorporate the legacy databases, the public databases floating around, as well as be able to use the existing tools. But at the same time, we want to promote the possibility of developing more modern tools that are inherently aware of the broad number of databases that are floating around there and the kinds of interfaces and ways to interact with these data. So this image shows a bit of an architectural diagram. At the bottom are the sort of raw data bits. These would be the SID grid native data taken in a sort of a SID grid kind of way. And these are the already existing and concurrently generated public databases made by other people. And the little arrows show sort of the connections through the architecture that will get tickled by various sort of uses of this overarching system. So a pure legacy use would be connecting the external database to the legacy tools that it was designed to use. A pure SID grid thing might be using raw data here and then carrying it up through interpretation through the data model, and then services that supply it to the users and to the applications that have been built on top of this service architecture. And of course, I've only shown one arrow. I mean, any one of these applications ought to be able to draw on data from all over the place, from many separate sources, and be able to seamlessly do comparisons. So, in order for us to think about what are the requirements in terms of the database building, the sensors, keeping track of the data, we talk about the kinds of data that these folks are going to want in their SuperLab. So this is a sort of a checklist of some of the most important sorts of data that they're interested in either generating or collecting in these laboratory spaces. The first little cluster are the sort of stimuli. And we intend to make available a variety of sort of pixel sources to meet the various needs. High resolution, transparent displays, screens that can show you 50% of projected material plus what's going on behind it for various augmented reality sorts of effects or comparisons between stimuli and reality. And then large projection spaces so that you can do things that require some sense of immersion. Audio feedback and spatialization will be provided by some speakers and things like this, and controlled by the computer systems that are part of the system. Video and audio, sort of access grid and beyond kinds of capabilities. Many cameras capable of taking in the scene, focusing on individual people, some very high resolution, high speed cameras so that certain time aspects can be taken into account, full body images, audio recording will depend on the details of the requirements of the experiment, but certainly ambient audio for some experiments, and then some that are very critical about making sure that they can do automatic analysis of the audio stream will probably require sort of local boom mics so that they don't get 1 over R squared issues that make it difficult to analyze the data. Usual kind of tracking systems, and we intend to buy these things off the shelf. Head-mounted eye tracking, a motion analysis, and a very cool little infrared camera, handheld, that catches sort of 8 microns to 14 microns at modest resolution, but at full frame rate for doing things like correlating blush reaction to facial motions and circumstances that are going on in the experiment. And then finally, a host or a raft, I'm not sure which, of physiological sorts of things. The first cluster of sort of most stuff is actually handled by a very small number of boxes, which are all integrated and just available. You get attached with sort of telemetry and bolted into the system. And then a very cool sort of high-density EEG system, which is typical for some sorts of these experiments, either 128 or 256 kind of registered points that get quickly loaded onto your head, and then those signals get, recorded and synchronized into the rest of the experiment. So this is a quick view of the projects that I described in one of the earlier slides against these various modes, the sensing modes, and which ones might be most appropriate for the various projects. Not much to take away from this except that these standard kinds of things, video and audio of various flavors, are likely to be very useful for most experiments. And then various connections depending on the details of what the kind of experimental area that's being worked on. Now, they'll all have in common a need to be integrated into the space, have their capture sort of sanitized in a way so that the data can be put ultimately into a database where we can understand exactly how to compare streams from each of these systems. Calibration, techniques for doing the calibration of the synchronization, the timeline and things like this will be bolted in and then provide information down here. And then all of this will be available to record and playback mechanisms that allow people to do the analysis and add annotations and things like this. So here is an overview of SuperLab. The stuff to the right of here is the SuperLab. It's more or less local to one position, one spot. So there's a physical laboratory space here, and it is instrumented so that a volume of it can be tracked very closely with the motion analysis and all of that sort of stuff, and that's represented by cameras on the edge of a sort of a polygon. And then in that space are intruding the various sensors that would be used for a given experiment. Here's a list of the sensor types and the acquisition system that is associated with each one of them. And back to this in a second. And then sort of off on the side, quite typically not actually in the same room, but in a room where observation can be made, will be a person who's in charge of controlling the experiment. Sometimes that just means sort of saying, okay, go. But other times it means actually interacting, watching what happens and pushing a button and causing a light to blink, or depending on the reaction of one of the guinea pig people in the room, causing some set of circumstances to change so that they can monitor the reaction to that. Underlying all of this stuff is synchronization. I'll get a little bit to that later, but the notion is that many experiments want to be able to test relative reactions in these various sensor domains down to sort of the biological limits, which is in the ballpark of a millisecond. That's kind of typical sort of time scales for firing paths and things like this. And so our goal is to make it so that we can, in some sense, capture all of this data, manage the time in a way that we can understand what's going on at about a millisecond time scale. So a few slides to run through quickly to sort of show how this space, I forgot to mention, on the right is the network interface to the rest of the universe, so that the implication there is that the data itself can live in a distributed way out in some grid set of resources that are wherever they have to be for whatever reasons, and then everybody who is allowed to and needs to and wants to has access to that in some useful way. So here's one instance of the way this kind of one of these rooms could be used. So this is an instance of one of those lab spaces. It's got a couple of people in there wired up to the hilt, and a guy sitting off there in the background kind of watching. All the sensors and the people are co-located, and this system allows control, monitoring, annotation, analysis to some extent in real time. and in particular archiving. All these streams will get saved off in an appropriate way. Another use is a sort of a remote now use of this system, in which perhaps the experimenters are off in Maryland, whereas this one critical resource, which is fairly expensive to set up, is sitting there and is running an experiment, has somebody in there who's been appropriately conditioned to grab the cheese when they're supposed to, and this person is giving them cues and monitoring and that kind of thing. So this infrastructure will support very easily this kind of a thing, with all of the fidelity basically that it would be if it was in the here now scenario. The distributed now scenario brings in one additional issue that may not have a solution. Locally, all of these sensors in this space can be synchronized very, very accurately, and locally in locale 2, the same can be said. Experiments that are intended to sort of be coordinated between these two places, where experimenters at one or both places are watching what's going on and doing things, they have one thing they can't really get over, and that is that these sensors and streams here can't be very easily sort of co-located in time, synchronized with these streams, just because the intervening network does, probably always will have some sort of latency that you can't get around. And there's a latency that can be as low as a couple of few milliseconds, which might be tolerable, but you can't rely on it, and that's the main issue. The latency can go up to hundreds of milliseconds if there's a glitch in the network at the wrong point. And then finally, one of the most important sort of advances that this architecture sort of allows is the sort of virtualization, and that is you can be anywhere after the fact. And this little bubble here is meant to represent sort of what's hiding out there in sort of the data stores of the SID grid. None of it's happening now, but as an experimenter, I can go poke around there and look at some, any, all of the experiments done at one place, multiple places, compare them, and do all kinds of new things with it. So here's a picture that shows a little bit about what has to be done to think about time in synchronizing these streams to meet that kind of 1 millisecond goal. But it also illustrates some of the sort of interesting relationships between data here and there. So locally warehoused data is up there, and other data is sort of down here. And for example, the annotation up at the top done by Mr. Square Guy on the local data, also done by Mr. Square Guy here, and warehoused locally, was done on remote data. Okay, Mr. Round Guy happened to be in a couple of places at one time. So he did some annotation here when the experiment was being taken at the place, and over there on that. And then, by carefully keeping track of each kind of an object, it's a description of the sensor system and the critical issues of how the timing is managed in that device. What are the frame rates, and some details about where the time stamping gets happened in the pipeline. Keeping track of all of that very carefully, then we can relate things that are meant to be related, like these three, by applying appropriate shifts in the time in case the system that collected this, collected that, don't have matched time systems. You can adjust it, store that number sorted here, and present to this level a perfectly synchronized trio right here. So that time tree is a sort of a scheme for after the fact, managing and adjusting and synchronizing data streams to get them all on a common timeline that's written on the bottom. So here's some of the issues that you have to think about when you're thinking about the time game. The device sampling properties that I mentioned, each one of these devices is measuring some property of reality over a particular amount of time, that signal integration interval, sampling at some rate. The data acquisition system, which is just after that sensing, is sometimes doing a data conversion. It's sometimes buffering some data and then looking at it depending on system interrupts, depending on the architecture of how it's connected into the data acquisition system. So there can be latencies, sometimes delays that are jittery that you don't know anything about. Time stamping, where in the process does the timestamp that's critical happen? Is it happening way up there? Is there something like a clock riding on the signal? Or is it happening way down here? Is the only timestamping available the stuff that's showing up on the RTP timestamps? And the network itself introduces timing issues. So we're thinking about all these things. So here's just an example of an idea that we're sort of working on actively in the lab. This is a representation of some issues in a video stream. But so at one instant in time, not one frame, one infinitesimal instant, that's the scene. Now, this video sampling profile is meant to abstract and simplify the idea that from this time to this time, the shutter's open and taking in light. So that scene is changing through that time, causing action in that scene to be smeared over that time. But if you know exactly what this window is, what time the start and the stop happened, and how long that gap is, you have a hope of pulling out of the smeared data some very detailed information if you can come to the table with a model of what you're looking for, like a moving pendulum, for example. It would be very easy to get some exact data on where it was at every single time in here, even though your fundamental piece of information is one integrated frame that gets handed to you as image that smears all that data. One way to get at that is to provide in the room a light metronome sort of an object which blinks at a perfectly known rate and phase. And you can see it's a different rate than the sampling right there. This shows up at the beginning of the frame here, and by the end of it, this blink is not even happening, okay? And by watching the signal from that blinker in the video stream, you're actually imposing on the video stream a sort of ideal signal that you can then pull out by beat frequency analysis, an exact phasing and timing for all of those little squares, with just a few assumptions about how accurate, how jitter-free is that edge. Is this a crystal controlled oscillator driving it or what? And simultaneously, if the time base that's generating this known thing, completely under our control, is also providing an audible tick every second or two, that tick is being picked up in the audio channels at 40 kilohertz or whatever, and it's easy to then synchronize automatically the audio with the video. So that's an idea that we're pursuing. But we're not hanging our hat on that alone. Some expensive systems have intrinsic to them Genlock or other sort of triggering mechanisms that are available that cause you to force time lock between like or somewhat like systems, subsystems. The TikTok stuff would be covered in these two bullets, carefully understanding the details of the object itself and possibly introducing an unobtrusive environmental signal that gets put onto the sense signal. And finally, for some of the signals, like an EEG, it might be possible to just drag one wire that's available globally in the room and snip one of your 256 lines and let it be a little time signal that goes along with it, so that the 256 data acquisition system automatically carries a time signal that you've generated that you know about. So that's been a bit of an introduction to what we're trying to do. And this is just a summary of why we're trying to do it. Again, it's about multimodal data and trying to get over some of the issues of making it so that we can collect these kind of new and interesting data sets in a way that preserves time properties, allows us to do detailed comparison, and allows us to archive these things so that we can create a new kind of experimental basis for doing social and behavioral studies. I'm not the only one doing this. These aren't the only people doing this, but they're the only ones whose names I could spell. And with that, I'll stop for some questions, if there are any.
I just wanted to note that I've heard people in the modeling and simulation field talk about exactly the same kind of problem. They're not talking about sensor data. They're talking about their models and simulations that run on very different time scales, and they need to try to integrate them all. And it's extremely hard to try to figure out how to do that.
Yeah, the way you're saying it, it sounds a little bit like these multi-scale problems and that kind of thing, where you You run simulations that are sensitive to very orders of magnitude different scales of the problem, and trying to make them somehow mesh the gears from these very different processes. Yes.
I would think you would have much that same issue where your EKG signal has a time mark on it that's just totally out of sync with what you'd be caring about.
And a lot of these signals have this property where the EKG, the audio, they're all being taken at fairly high sample rates, and so they're very easy to get into that 1 millisecond range. The video, well, I mean, you can go buy very, very expensive, very high-speed cameras and generate a lot of data. That's not always necessary, and I think that even commodity systems, if you look at them a little bit carefully, can be retrofitted in a way, in this kind of a way that I'm describing, so that you can extract certain kinds of model data down to that ballpark of millisecond timescales. Okay. Thank you.